In our last few lectures, we have been studying about different techniques which can be used to design our logic networks. So up till now हम जो टेक्निक पढ़ते आ रहे हैं उसमें हम सिर्फ लॉजिक 0 या लॉजिक 1 लेवल की बात करते हैं. ईदर लाइक वी आर कंसिडरिंग अबाउट लाइक इनपुट इज like logic 1 or logic 0, or we are only considering our output as a logic 1. For example, we are talking about designing the NAND gate in a single circuit, but we are not talking about designing two different networks in a single circuit. So this can be achieved using this dual rail logic networks. In our dual rail logical networks, we have non-inverted input and we have inverted components exist simultaneously. Like we have two different inputs or two different outputs, which are like, for example, in a simple example, we have a NAND gate and a NOR gate. And similarly, we have multiple inputs, and those inputs are like one is our straight input and the other one is our inverted input. For example, we have these two variables x and y, x and x bar. So the function works for both these variables, like this the output function f of x that represents that works for both variables. So this provides basically an increased switching speed, and we can also achieve the complementary output as well. So the drawback of this technique could be one drawback, that is like increasing complexity and obviously area overload. हमारे पास इसमें दो तरह के ड्रॉबैक्स हो सकते हैं. एक तो ये कि ये डिज़ाइन थोड़े से कम्प्लेक्स होते हैं फॉर डिज़ाइनिंग. लाइक जब भी आप डिज़ाइन कर रहे हो अपने नेटवर्क्स को, तो अपने लेआउट डिज़ाइनिंग में ये कम्प्लेक्स हो सकता है, लेकिन इसका जो एरिया ओवरहेड है वो भी इंक्रीज़ हो सकता है. लेकिन इनको लाइक अंडरस्टैंड करना और इनको डिज़ाइन करना फॉर डिफरेंट योर एप्लीकेशंस इज़ ईजियर एज कम्पेयर टू योर अदर नेटवर्क्स. फॉर एग्जांपल, this is our dual rail logical network. This is known as cascade voltage switch logic, like CVSL logic. So in this logic, we have like two different pull down networks. Like here we have one network that is represented by switch 1 and the other one is our switch 2. अब इन दो नेटवर्क्स में जो डिफरेंस है वो ये है कि हमारे पास जो इनपुट्स हैं, अगर आप यहाँ पे ऑब्जर्व करें, जो हमारे पास इनपुट्स हैं A, B बार एंड C, इसकी जो कम्प्लीमेंट्री इनपुट्स है वो यहाँ पे होंगी. लाइक अगर यहाँ पे A है तो यहाँ पे जो यूज़ हो रहा है वो A बार है. सिमिलरली अगर यहाँ पे B है तो यहाँ पे B बार यूज़ हो रहा है, यहाँ पे C है तो सिमिलरली C बार यूज़ हो रहा है. तो ये आपकी कम्प्लीमेंट्री इनपुट्स है. अब ये ऑपरेट कैसे करता है, इसके ऑपरेशन मोड जो है वो ये है कि आपकी जो आउटपुट्स हैं वो दो तरह की हो सकती हैं. एक आपकी आउटपुट जो है वो F होगी, दूसरी आपकी F बार होगी. दोनों आउटपुट्स जो है वो एक लेवल पे नहीं हो सकती हैं. लाइक इट मीन्स लाइक इफ f इज इक्वल टू 0 देन f bar will be equal to 1, and this is basically controlled by this latch circuit here. This latching basically procedure, this latch basically adds the control of this inverted output. So for example, we consider a simple dual rail logical network. So we are considering this network here. And for example, if our switch 1 closes, that means if due to this network here, like these three inputs here, हमारे पास ये जो switch 1 है ये close हो जाता है. If switch 1 close होता है तो it means this point here is connected to ground. और इस point को ground से connect करने के बाद हमारे पास क्या होगा कि अगर ये ground हो जाता है तो it means this point is 0 now. If this point is 0, then this PMOS will be turned on, and if this PMOS is turned on, it means this is now connected to VDD. So अगर हमारा switch 1 closed है, F की वैल्यू 0 है और ये PMOS हमारा ऑन हो जाता है. जब ये PMOS ऑन हो जाता है तो ये उसको क्या कर देता है, उसको 1 कर देता है. अब इसको अगर आप यहाँ इस लैच में यहाँ पे देखना चाहें तो ये अगर 1 है, ये वाला पॉइंट, तो ये हमारा PMOS जो है वो क्लोज होगा. ये हमारा ओपन होगा. तो हमारा देयर इज नो डायरेक्ट कनेक्शन बिटवीन VDD एंड F आउटपुट. So this is our like inverted output. And similar behavior obviously can be represented or can be described for the switch 2. Like if our switch 2 is closed, this goes to 0, this goes to 1, and similarly this is open circuit here. So this is our like CVSL networks. So now let us solve an example, or we can understand these two networks. This network using an example of a NAND gate, and then we will move to a complex equation or complex the circuit. Then we will see how can we design a network using CVSL, and how can we reduce the number of transistors using CVSL networks.
So there are several ways to design a large network. The simplest approach is to design separate circuits for left and right sides. A simple rule to remember is, like, while designing CVSL networks, we use pair of complementary input and outputs. So we take a simple example of our NAND gate design. In this NAND gate design, like, we first start with one operation, that is our operation of right side, and where we take the same example or same the solution which we have been studying for our CMOS gates. So the right hand side of our design would be the right side. This would represent a simple CMOS operation, and this is designed using pull down network, or we can say that using our NMOS. So if I draw the right side would be something like, let me draw the upper portion first. We have one PMOS here, we have one PMOS here. These PMOSs are similarly we have one output at this node and one output at this node. This one is connected to this point here, and this one is connected to this point here. So this represents our F, and this represents our this represents our F bar, and this represents our F. So it means one is our F and the other one represents the inverted output. So we are designing a NAND gate here. It means if we consider F is equal to NAND, if F is our NAND, then this will be our F and this will be our F bar. So to design the right hand side, we know that the pull down network of our NAND gate was equal to this, two series connected NMOS. This is our A and this is our B. If we have to design the left hand side of our this CVSL network, we just have to apply the De Morgan's law on the right side. So what we have to do is apply De Morgan's law on right side. Which means A dot B NAND, this should be equal to A bar plus B bar, and then we have two inputs, one is our A, one is our B, and both are connected in parallel, we can check from this point. Now, so we have two NMOS, these are connected at this point here. One is our A bar, the other one is our B bar, and these are connected to ground. So this is our network, the network which is known as the CVSL network. So to design these switching networks, logic trees provide more structured approach. We can use the logic trees to basically design these networks in a simpler way or in an easier manner. And we have to design using logic trees. We have seen one equation earlier, that equation was we have seen this earlier, that if we want to write equation or the right expression for NMOS given below. Like for example, if we have this NMOS here, we have seen earlier like this expression, like this is X and this is A, this expression would be X dot A. We basically have to use this simpler approach so that we can like write the networks. So from now on, in this designing approach, in this video session, I will not be using the latching circuit, the latch circuit that provides the connection to the VDD. We will only be designing the complementary pairs. So you can assume that there is the latch up circuit is present by default. For example, let us take a simple example here. If we connect two NFETs like this one, if we connect one NFET here and one NFET here, and this is our common point, if our inputs are like this is X and this is Y, this is A and this is B, so sorry, this cannot be A, this cannot be A and AB, this should be alternating inputs, that is A bar and A. So if we analyze this expression or this circuit, this represents our 2 to 1 mux. Like this circuit, this CCT represents 2 to 1. Why this is representing our 2 to 1 mux? Because this side here, this represents A bar dot X and this side represents plus A dot Y. Like it means only one can be transferred to the output or to the can be transferred to this node here, like either X or Y. We cannot transfer both at the same time. So this is a simpler circuit, a simpler logic which can be used to model our 2 to 1 mux. Let us now consider a bit complex example, a bit complex circuit that can be represented by a truth table. Or if you are given with a truth table, then how can you design your circuit? So an example example is like design using the function table. The function table given here is like our function is f. We have two inputs A and B. F is like the outputs are 1, 0, 0 and 1, and our inputs are 0, 0. We have 1, 0, 0, 1 and 1, 1. If we analyze this function here, this basically represents XOR gate. This represents an XOR gate when our f is equal to 1, like the function is 1, and obviously CVSL represents two logics. The other logic will be f is equal to 0, and this will represent XOR gate. So the equivalent circuit of this table here, this table, can be drawn by looking at this table. So the equivalent circuit has two levels now because we have two inputs. This can be drawn easily. So for example, if we look at this table here, we can see that we have when our input is 0 and when our both inputs are 0, this node represents an one output, or we can say this is connected to one output. For example, let me draw first both two stages and then we will connect to f is equal to 1 or f is equal to 0. So our both stages can be drawn something like this one. This is our stage 2, that represents our B's. This is our B, and then we have this stage here, this represents B bar and this represents B. These are common here, and we have the stage 1 here this represents A bar, and this represents A. These are connected to ground. Now we have to decide which paths connect to F1 and which path connects to F0. For example, our F path, F line is this here. This represents F is equal to 1, and we have a second line which represents F is equal to 0. Like we have the second line here. So this represents XOR and this represents XNOR. So by looking at this table, if we look at first line first, we have A is equal to 0 and B is equal to 0. That means A is the inverted input and B is inverted input, and this is connected to our F1 here. So we have to connect the first line. We have to connect this first line to F1 that is connected here. Then we have 0 and 1. A is 0, B is 1, that is connected to 0. It means A is 0 like this line, and like we have to track out this line here like this one here. So this is connected to 0. So it means I can connect this point here to 0. Then we have this third line here, this one. We have 1 0. It means A is 1, B is 0. This line is connected to this is connected to 0. Similarly, the last line is connected to 1. So this is the simplest way that we can design our network. So these networks are very easier to design, easier to simplify the circuits, and easier to understand. We can take another example where we may design a little bit complex network, and we also simplify that. And one thing to understand, or to basically make the designs easier on paper, we use one convention, and we will apply that in next example or next exercise. The convention is like this network here, this one. This network here can be replaced by a block minus and plus. This minus represents, this is our B bar, and this represents B, and this can be replaced by minus and plus as well, and this the lower part can also be replaced by minus and plus. So we can say that this negative is connected to this point here, this positive is connected to this point here. We have two outputs from this source, two outputs from this source, and both are connected on different lines that we can connect as we have done it in this upper portion. So this is a convention that we can use to simplify the networks on our paper design. So we consider a next example here. In our next example, we have been given with a function. Like this function is a little bit complex because it represents 3 inputs. So the function is like f, a, b, and c. And we have the first output, that is 1, and we have 1 like these these are two outputs. Then we have 0 and 1, we have 0 0 here, and we have 1 and 1 here. Our inputs are in order like 0 0 0. Then we have like 0 0 and 1, we have 0 1 0, and we have 0, sorry, this is 0 1 and 1, and then we have 1 0 0. Basically this is a group of 3. Then we can make it a group so that we can read it easily. This is 1 0 and 1, we have 1 1 and 0, and then 1 1 and 1. So this is our table that we have to design for the CVSL network. By looking at this table, we can say that we have 3-level design. In our 3-level design, we have to make make a stack of our this inverting and non-inverting NMOS. So to make it simpler, we will use the convention, the plus and minus signs. So starting from this bottom level, we have this minus and plus sign here. This is connected to ground. This means this will be connected to like negative and positive, and this will be connected to like negative and positive. So these are our two levels. The next level is this will be connected to another negative and positive, and this will be connected to another negative and positive. Similarly, this will be connected to another point, and this will also be connected to another point here. So the outputs, like the outputs can be connected to these two lines here, like one is our F line and one is our F bar line. We represent this as F is equal to 0 and this is as F is equal to 1. So we have these outputs 1, 2, 3, 4, 5, 6, 7 and 8. We have 8 outputs. Now we have to look at the table and we have to connect these lines. So if we look at this first line here, this is connected to 0. This is basically connected to this is connected to like 0 0 0 line. This is 0, this is 0 and this is 0. This is connected to 1. So it means I can connect this point to like 1. I forgot to mention one thing, like this level represents A, this level represents B, and this level represents C. So we have all these three different levels. So we have made our first connection. The second connection is 0 0 1, that is connected to 1 as well. So the second connection is 0, like this one is 0, this one the next one is 1. Sorry, A is 0, B is 0 and C is 1. So this is our connection. This is connected to 1 as well. Similarly, we have the next point here, this one here. This is connected to like 0 1 0. It means 0, we have next 1 and then we have another 0. So this is the path now, like 0 1 and this is 0. So we have this path here. This is connected to 0. And next we have the next path is it is like here 0 1 1. So it means the first one is 0, the second one is 1, the third one is also 1, and this is the path. So this one is connected to 1. And similarly, we can continue this and we can connect all these points. The next point is connected to 1 0 1 0 0, that is connected to our like 0 level. The next one is connected to our 0 level. This one is connected to our 1 level, and this one is connected to our 1 level. So this is our circuit. Like this is our circuit that we design by looking at the table. But one thing to know here is, like, we can simplify the circuit, and it is very easier to simplify the circuit. For example, you can see, like, if you observe this point here, like this point is basically representing, like, either it is like C bar, sorry, either we have C or we have C bar, both are connected to 1. So it means if we skip this point here, we can directly connect this point to this point. There will be no difference because this is connected to 1 in any case. Either we are using C or we are using C bar. This can be observed from the table as well. If you look at the table, you can see here, like in this table here, you can see, like, if our function is 1 1, like if our function wherever our function has 1 like common output, we have to observe what thing is changing, what thing is changing here. So I made a little bit mistake here, like this is not like A, B and C. These are like C, B and A. So this makes things clear now. So for example, if our like output is 1 1, we have to observe below that, like the inputs. Wherever our input is different, we can ignore this output level, or we can ignore this block here. Similarly, if you observe here at this point, we have these are inputs are changing, and these two are same. At this block here, this input is changing and these two are same. So it means we can ignore these 3 points, like this one here, 1, 2 and 3. We can ignore these 3 blocks and we can bypass these outputs, because these 2 points, these 2 wires and these 2 wires, like these 2 wires are connected to 1 and these 2 wires are connected to 0. So we can ignore these 2 paths, and the simplified final circuit would be a little bit different. Like if I draw the final circuit here, that will be like this will be equal to, if I have to basically remove these 2 points here, and I have to remove this node here. So this was RB, and the simplified circuit would be, this was connected to 1, this was connected to 0, and this was connected to 1. So what we have done, we have basically removed 2 NMOS from here, we have removed 2 NMOS from here, and we also have removed 2 NMOS from here. So we are left with like NMOSes, which are 2, like 1, 2, 3, 4. We have total of 8 NMOS now, instead of like we had 14. And similarly we have PMOS which are in latch up. These are 2 PMOS. Like we have in total like 10 gates. So this is our design where we can use dual rail network, and we can design our circuits in a simpler way. So we can say that the CVSL networks are easier to implement and are more easier to simplify. So this was our final discussion for these CVSL networks, and this is it for this session. I hope I will see you in next session.